So good evening everyone and welcome to our first official lecture of SCI 154. I hope that you guys enjoyed last night's introductory lesson. And do you guys have any questions so far? Any administrative issues I need to sort out for you guys? Okay, so one thing I did with the class last year as well is I would like to begin this period by asking a general question of what's what is something interesting you have read or heard about space sciences last week? Okay, so I would say the last month is, yes, Perseverance rover landing on Mars. That is an amazing achievement from the guys at NASA JPL. And then what do you mean with invisible stars? Yes, Starlink is also cool, but you know Starlink is a big problem for astronomy in general. So Starlink is a problem for optical telescopes and radio telescopes. In optical telescopes, the Starlink satellites reflect a lot of sunlight, and we can pick that up with the optical telescopes. So if you are observing something and Starlink satellites move across, then it can ruin your image. And then in radio telescopes, the Starlink satellites operate at a frequency of roughly 5.6 gigahertz, and we do observations of radio telescopes from 5 gigahertz to 7 gigahertz. So that means it blinds us in a 5 gig range, which is also a big problem. So currently the international astronomy community is having discussions with SpaceX to see if there's a way that we can solve this problem. So let's see what tonight's lecture is going to be about. So in tonight's lecture, we're going to have an introduction to what is the nature of astronomy, the nature of science, laws of nature around us. How do we comprehend different numbers in astronomy? Numbers such as distances and sizes. Then we're going to have a philosophical question of where are we and the universe, how we fit into the scale of the universe, and then a little bit of history of astronomy and some of the most important discoveries in astronomy till this point. So something I'm going to encourage you guys on, because you are scientists, is to just every week, you don't need to read full articles, but just try to pick up some of the interesting stuff happening out there. It really helps you to build a nice database of knowledge. And one thing you will also pick up with my lectures, there will be a lot of Windows bashing in my lectures, because if you are astronomer, scientist, or engineer, you stay away from Windows and use Linux. Can everyone still hear me? Okay, so we're going to start off this lecture with what is the nature of astronomy. So astronomy is defined as the study of the objects that lie beyond our planet Earth and the processes by which these objects interact with one another. it's all, I can see the class is very quiet this evening. I like it when a class is interactive, but I know you guys are tired. This is one of the last periods of the day. But let's try and keep this class as interactive as possible. You can use the chat to ask questions. You can unmute your mic and ask questions if you guys can. And you can take it from there. Say, see, here's a problem hearing me well. Let me see what I can do about it. Okay, so I'm testing my input levels. So my input levels on the mic is currently at maximum. Okay, so with the astronomy definition of astronomy that we have, it's all fair that we observe these objects in space, but it is also important that we understand what governs these objects, what makes them tick, what rules of physics and nature does these objects follow. And then I also ask usually a question to students, and this is a question I get asked often, is why is astronomy important? Why do we do astronomy? Do you guys have any ideas? Okay, so see, one asks, it's fun to help us understand our place in the universe, to understand why things are the way they are, to understand the universe better, space exploration, to understand where we come from. Humans are nosy, and that is the answer I'm looking for. So if you generally think about astronomy, why do we do astronomy? What does mankind learn or gain from doing astronomy? So the short answer is astronomy, what does it contribute to our everyday world? Not really much. Instead, there can be sometimes technology coming from it, but us as humans are a very curious species. We want to know what is out there, how stuff works. It's the same going back a couple of hundreds of years when humans started exploring the globe. And it's the same why we explore the deepest parts of the ocean. We want to know what is out there. And by developing the methods to study what's below the oceans, what's in the sky, what's in space, we contribute to human society in a form of knowledge and technology. And yes, that also brings us to a philosophical question to where is our origins? So, through this module, and especially in this chapter, we will realize that astronomy is much more than just observing objects. It is also humanity's attempt to organize what we learn into a clear history of the universe, from the instant of its birth in the Big Bang to the present moment. In considering the history of the universe, we will see again and again that the cosmos evolves. It changes in profound ways over long periods of time. For example, the universe made the carbon, calcium, and the oxygen necessary to construct something as interesting and complicated as you. Today, many billions of years later, the universe has evolved into a more hospitable place for life. Do you guys know what this image is, or can tell me what this image represents? So yes, I see a few answers. The Big Bang, expansion of the universe, a timeline, the universe, the cosmic timescale, universal expansion. So you guys are all correct. So this is our time scale and representation of our known universe, of where it began, how it expanded to where we are today. So from the physics that we understand and know, everything started with the Big Bang, and that is 13.8 billion years ago. And when the Big Bang happened, it started with the cosmic dark ages. That is 380,000 years after the Big Bang. Then, after 180 million years, we get the first stars. After 250 million years, black holes and accretion disks. Then we get reionization, modern galaxies, and then 13.8 billion years later, where we are today. So, something interesting to think about, fitting into last night's lecture. Usually a black hole will evaporate, but until this time, no black hole has evaporated yet. So that is something that we still need to observe and see. And the math points out that our universe is still too young to see black holes evaporating. So what is the nature of astronomy? So in astronomy, we look at the history of how everything evolved until today. So we have the Big Bang, Dark Ages, first light, and then where we are today. So, question, do you think humankind will ever see such? Yes. So that is why it's important for the human species to become an interstellar race so we can guarantee our existence. So question, how do we know that black holes evaporate if it hasn't happened yet? We can observe black holes in a few ways. So one is by observing the event horizon around a black hole and then doing math on it. So we all know that according to physics laws, and we know that matter cannot be created nor destroyed but can only be transferred from one form to another. Black holes is getting smaller over time, but it takes billions and billions and billions of years. So currently the black holes that we know exist are very young black holes. So now question, how long do you think it will be till the human race becomes interstellar? That will be in the 2030s. SpaceX aims to go to the first human on Mars in 2030. NASA aims for 2034. Boeing aims for 2032. I know the European Space Agency want to go, China want to go, the Russians want to go. So has a black hole ever evaporated before mankind? No, because our universe is too young for it. Right now we are currently at 13.8 billion years. So first light appeared 560 million years after the Big Bang. So we can roughly say the first stars are at 3 billion years old. And so some of them died out, became a black hole, and those black holes need to go on for billions of years as well. So currently no black hole has evaporated yet. So another question, how do we know that the mathematical models created by the physicists and other astronomers are the same outside our galaxy? So that is a really good question. So that's why we construct these mathematical models. So for the math to be 100%, we have to assume and to prove that the math is the same everywhere in our universe. So in our universe, everything has to be the same, but then we start going into the multiverse theorem and paradoxes that laws of physics might be a little bit different in other universes, but that is where the math becomes quite boggling. So question, how did a Big Bang happen and why did it happen? When did it, and sooner or later? So that is a question that we don't know. So that's why we as astronomers and scientists need to answer those questions. So what do you guys think is, let me go back the slides and then give an answer away. So what do you guys think is the nature of science? Yes, to explore. Any more suggestions? Yes, learn from questioning, to understand, prove something, to question the nature, curiosity. Yes. So, the ultimate judge in science is always what nature itself reveals based on observations, experiments, models, and testing. Science is not merely a body of knowledge, but a method by which we attempt to understand nature and how it behaves. This method begins with many observations over a period of time. From the trends found through observations, scientists can model the particular phenomena we want to understand. Such models are always approximations of nature, subject to further testing. So, a question, do astronomy align some of the answers with religion information? So that is a lot of philosophy. So generally in science, we try not to bring religion into it. We try to have separation between religion and science because we want to be able to test things, do observation, create mathematical models, and some historic documents is not the most accurate. So there's usually a distinction between that line. So what do you mean with theory? So if we start looking at the nature of science, we need to make some sort of observations because in the Middle Ages and even earlier than that, it was believed that Earth was the center of everything. But we determined so that it looked like Earth was the center of everything. Everything is moving around Earth because we see the stars coming up, the stars setting, the planets coming up, the planets setting, the sun coming up, but the sun setting. So we create a model around it based on our observations and the knowledge we have available. But these models can be subjected to change as we understand them better. So the Big Bang theory is called a theory, but it's not considered a theory anymore. It's the best explanation we have of how everything started. There are a few other theories as well, but the Big Bang theory is now considered the rule. So yes, Ptolemy. So yes, Nicholas Copernicus. The prime mover, so let me go back to the previous slide. Okay, so sphere of the prime movers. So it was just the model that we have. So in our reference frame, we are the prime mover and everything moves around us. So The next model we have is of the sun in the center, and everything moves around the sun. So that's why when we can observe nature and construct models, as we understand the nature and phenomena better, we can adjust our model better. So going back one slide, we know the Earth is not at the center of everything, but a couple of hundred years ago, this was based observations, seeing, okay, everything moving around us. But then we start doing other observations and we realized, okay, we are not the center of everything, we are moving around the sun. And then we can also see, okay, some of the other planets and objects in our solar system also moves around the sun. So, when they are first proposed, new models or ideas are sometimes called hypotheses. You may think there can be no new hypotheses in science, such as astronomy, but everything important has already been learned. Nothing could be further from the truth. So, some of these new hypotheses that we are asking ourselves is, what is dark matter? And another question is what is the origin of life? How did life start on Earth? So resolving these issues will require difficult observations done at the forefront of our technology. And all such hypotheses need further testing before we incorporate them fully in our standard astronomical models. So in your scientific careers, you will learn a lot about the standard model or standard astronomical model. So the standard model describes how everything fits together. So the standard model includes everything we know from physics and math this far. So the standard model explains Newtonian physics, Lagrangian physics, quantum mechanics, time, space-time, general relativity, special relativity, and everything needs to fit in together. So the standard model is what we go against. So the last point is crucial. Hypotheses must be a proposed explanation that can be tested. The most straightforward approach to such testing in science is to perform an experiment. If the experiment is conducted properly, its results either will agree with the predictions of the hypothesis or they will contradict it. If the experimental result is truly inconsistent with the hypothesis, the scientist must regard the hypothesis and try to develop an alternative. If the experimental result agrees with the predictions, does not necessarily prove that the hypothesis is absolutely correct. Perhaps later experiments will contradict crucial parts of the hypothesis. But the more experiments that agree with the hypothesis, the more likely we are to accept the hypothesis as a useful description of nature. So, what do you guys think I'm planning with this slide? So this comes due to an age-old example in science. So what colors do you think generally sheeps are? Yes, white sheep. So what does the model of sheep tells us? All sheep must be white, but there are black sheep as well. Certain species of sheep are black. So when we create our model, we know, okay, we make the hypothesis that all sheep are white. But when you go into nature and start defining more and more sheep, here and there we will find a black sheep. So what does that mean? Does that contradict our hypothesis? Do we change our model? What do we do? Yes. So our model needs to be adjusted. And that's how science works. So that means, okay, our hypothesis is disproved, but how do we adjust it? So we change the model to fit in the black sheep. So that's how science works. So now we know we can also find black sheep in nature, and now we need to readjust our model. So now if we go back to our model and we say, what color can she be? We know the majority will be white sheep, but it can still be black sheep. And so our model is updated. And we can use this principle anywhere in science. So, astronomy is sometimes called an observational science because we observe everything in space. And much of astronomy is also a historical science. So why do I say it's a historical science? So question, would an adjusted model make you closer or further away from a conclusion? That will make you closer to a conclusion because we now have more data available to us. So, why is astronomy a historical science? Yes, you are correct, Mr. Groenewald. The time scale of events are over multiple lifespans. So if you ever think about what's happening in the scale of our universe, the universe is one. You can give the example. The universe is a one big laboratory where experiments takes millions of years. So astronomy is also historical science because it takes long for things in space to change. So we need to look at our data we have now and correlate it to data from the past to see what's happening. So, question, so data from past useful? Yes, data from the past is extremely useful. For example, I can give you a practical example I'm working with. So if you observe mazes in space, we have data going back to the 1960s. So when we observe an object that's been observed multiple times before, we look to the previous observations and see what has changed. So, number one. So, why do stars twinkle like that? Is there a scientific reason? Yes, that is due to the atmosphere. So, how many galaxies has been discovered? Thousands of, I'm not quite sure on the number, but I think it's millions of galaxies has been discovered this far. So before I'm going on to this slide, so are the asteroids remains of a planet which broke apart? The answer is yes and no. In later chapters, that is something we are going to discuss in depth. But the short answer to that is usually when planets start forming around a star, we call that a planetary disk. And particles start to clump together. So some of them forms planets, some doesn't and it becomes an asteroid. Something happens like some of these planetoids that's being formed can bump into each other and break off. Objects can come into a solar system, be caught in a gravitational field around the sun. So there's a lot of different ways asteroids can be formed. So what do you guys think about, or who can explain to me what is the laws of nature? So everything that lives dies. Yes, that's the law of nature, gravity. And that's the one I'm looking for, is their constant. So that means if we have a law of nature, it has to be the same everywhere else in nature, so everywhere else in our universe. That is important because if there can't be a law for a certain part on Earth, our nature operates in a law on the second part of Earth, then we have a big problem. So, over centuries, scientists have extracted various scientific laws from countless observations, hypotheses, and experiments. These scientific laws are, in a sense, the rules of the game that nature plays. One remarkable discovery about nature is that the same laws apply everywhere in the universe. The rules that determine the motion of the stars so far away that your eye cannot see them are the same laws that determine the arc of a baseball after a batter has hit it out of the park. Note that without the existence of such universal laws, we could not make much headway in astronomy. This is not to say that our current scientific models and laws cannot change. New experiments and observations can lead to new, more sophisticated models. Models that can include new phenomena and laws about their behavior. The general theory of relativity proposed by Albert Einstein is a perfect example of such a transformation that took place about a century ago. It led us to predict and eventually to observe a strange new class of objects that astronomers call black holes. Only the patient process of observing nature ever more carefully and precisely can demonstrate the validity of such new scientific methods. So, let's go back one slide. What do you guys think? What can you tell me about a black hole? What is a black hole? Not planets that die off, but that is a dead star. So we're going to discuss how this is formed in later chapters, but yes, it's a dead star, more precisely a collapsed star. So, a black hole is a region of space that is so intense that no matter or radiation can escape it. So, the laws of nature. So, going to black holes. So, in 1915, Albert Einstein developed the theory of general relativity, where the theory shows that gravity influences the motion of light. So in these images, we can see an old Albert Einstein and a young Albert Einstein. So please repeat, what is a black hole? So a black hole is a star that collapsed in on itself. So, okay, go back one slide. So this is so what happens when black holes finally evaporate? So that I don't really know about. That's not my field of expertise. Um, Probably in your third year, you will run into Professor Roger Dean. He is he was part of the team that captured the first image of the black hole. So black holes are his speciality, and he will be able to answer the questions better than me. But let me try and answer a few of the questions. So singularity. So yes, that's a term given also to a black hole. So usually when a star is at the end of its life cycle, it collapsed on itself, it becomes a singularity. So think about it, so the gravity surrounding it is much stronger. Not really. So if you think about a star that collapsed on itself, the mass of the star, meaning the gravitational pull around the star, is the same. So if the black hole collapses on itself, the gravitational pull in the area remains the same. The only difference is when it becomes a singularity, you can think about it that it starts eating matter that comes too close to it. So if you think about our own sun, our own sun also has a event horizon. So that's the area, the imaginary line. If you get too close or cross that line, we won't be able to escape the gravitational pull of our own star. So the same thing happens with a black hole. So the gravitational pull remains the same. So can you explain why the sun is actually white in color? So that is something we're also going to discuss in upcoming lectures. But the color of a star depends on how large the star is, how warm the star is, and what fuel it's currently fusing. So that's something we will discuss in later chapters. So do we have a planetarium at our university? So unfortunately we don't have a planetarium at UP. Currently there's only 3 planetariums in the country. The one is at Wits University, there's one in Cape Town, and there's one in PE, I think. So yes, all stars have a event horizon. Earth also has a event horizon. So Earth's gravitational pull is not as strong as, for example, a star, but if we don't have any sort of propulsion like rockets, if you come to a certain distance from Earth, you will also not be able to escape the gravitational pull, but now we have rockets that's powerful enough that we can achieve escape velocity and break free of the event horizon. So all stars have event horizons, all planets have event horizons. So what is the difference between an event horizon and a sphere of influence? Sphere of influence is a term I haven't heard before. So what can you tell me about the sphere of influence? So when we continue on to the next slide, we can see here a young Albert Einstein and a old Albert Einstein. And this is one of Einstein's incredible equations, and that is the field equation for general relativity. This is not something you need to know right now, so this is something you will learn in your 3rd year. But this is just something interesting I thought to show you guys. And yes, his birthday was on Pi Day. So, before continuing on with the laws of nature, what do you guys think is the limitations that we have with the laws of nature? So, speed of light, yes, we are coming to that as well. So, from Mr. Clark, so I think the sphere of influence is the area that a body is affected by another body's gravitational pull, but maybe terminology is wrong. I'll get back to this answer for you. So to repeat the question, what do you guys think is the limitations of the laws of nature? So if we want to see what are laws of nature, what nature is doing around us, what is our limitation? So yes, we can't control it. So they were merely created with what we were able to observe and can change. So wrapping it up in a term, so can I control them? What we can observe, we can come down to language limitations. So if we observe something in the universe, something in nature, and want to have law of nature, how can we explain it to someone? How can we encapsulate it in a definition? So, going back a few slides, this slide. This is a law of nature, and what is the language we use to understand this law? Yes, it's math. So from this point on in your life, I don't want you to think of math as math. I want you to think about it as a language, the language that the universe speaks to us. And the best way to understand a language and to learn a language is to practice it. So that's why you do all these math modules, is to provide you with the knowledge to understand the language that a scientific world speaks. So there will be maths in this module. So the maths in this module is not hard. You will be able to do this math with your high school math. That's nothing to worry about. So if we look at numbers in astronomy we deal with distances on a scale you may have never thought about before, with numbers larger than any you may have encountered. We adopt two approaches that make dealing with astronomical numbers a little bit easier. So I'm sure you're all familiar with this diagram. Okay, cool. So are you all comfortable with scientific notation? So see here, what is the C? So let me go back one slide. So C is just a space that encapsulates everything. So scientific notation, we can go from 1 millionth up to 1 trillion. So before going on to the next slide, how far do you guys think is the Earth away from the Sun? Without Googling it, I want you guys to guess. Okay, oh, so guys know about AU. So what is the definition of AU? Who can tell me what AU is? The average distance from the Earth to the Sun is roughly 150 million kilometers. So 150 million kilometers is called one astronomical unit. And that is the SI unit we will be using in astronomy. I'm impressed so far with you guys. So it doesn't help that we speak about it's 150 million kilometers away, because that is very fast. So if you think about what is the distance from the Sun to Mars, that's roughly 225 million kilometers, so 1.5 AU. But Mars is further away from, so you have Mercury, Venus, Earth, Mars. So the distance from the Sun to Mars will be larger. The distance is not constant because let me see if I can get a whiteboard to work here. So if you think about this is the sun. Let's give it a little bit of color. And the orbit around the sun is not precisely circular. It is oval. So this is just a bit exaggerated. So we can say more or less this is, say, more or less 148 million, and this is more or less 154 million. So that's why we say, just from sucking these numbers, is more or less 150 million. And that's the same thing with other planets as well. We don't have a precise circular orbit around other planets. So we say 1 AU is 150 million kilometers. We take the average of these two. So it is an exact number. So let's get back to the slide. I'm just searching for the correct slide. So the oval shape is a consequence of the uneven distribution of mass in the sun. That and also the distances where our planetary disk formed and where planets formed as well. So think about AU. How far do you guys think is Saturn from the Sun? If you don't Google it, just guess a number. 1000 AU, that's a little bit big. 7 AU, close enough. So that's around about 9 AU away. But if we go beyond our solar system, the AU becomes quite a small number again. Then we move over to the light year. So the light year is the distance light travels in 1 year. So the speed of light is 3 times 10 to the power 8 kilometers per second. So I see there's a typo made here in my slides. I will fix it. So if we go to the light year, it takes light from the moon to Earth 1.3 light seconds. From the sun to Earth 8 light minutes. From the sun to Neptune 4 light hours. Our closest star to us, Alpha Centauri, that's part of Proxima Centauri, is roughly 4.2 light years away. So that means light from that star takes 4.2 years to reach us. We go to the star Polaris, 433 light years away. The center of our own Milky Way galaxy, 100,000 light years away. Our closest neighboring galaxy is Andromeda, that's 2.5 million light years. So should we know this diagram now? No need to know this diagram. This is just to get you guys comfortable with the numbers we are working with. So you guys all happy with astronomical unit and light year? You guys have any questions so far? So what do you guys think will happen when the light year becomes a small number? So will the AU be tested? Yes, the AU is tested. We know the distance from the Earth to the Sun, and that's why the AU was selected. So how are we able to calculate how far everything is? We will come to that later in this lecture and also in our following lecture. Not a light decade, but if we start going to larger distances, we go to a parsec. So I'm sure a lot of you has heard about the term parsecs in sci-fi movies and shows. So just something a bit off topic, in Star Wars, in episode 4, in the bar on Mos Eisley, when we meet Han Solo the first time, it says the Millennium Falcon did the race in 12 parsecs. Parsecs is not a measure of time, it's a measure of distance, so that's one thing Star Wars got wrong in physics. Yes, the Andromeda Run. So when are we going to use when the parsec comes to small? That's going to be our next slide. So how do we define a parsec? So let me read the definition, then I'll explain it. So if the angle suspended by 1 AU is 1 arc second, the distance is defined as 1 parsec. Astronomer can measure angles very accurately. Full circle is 360 divided by 1 degree divided by 60 parts gives arc minutes. 1 divided into 60 parts gives arc seconds. So, say for example, we can get into a spaceship and get far away from Earth. So here we can see, if we get far away from Earth, here's our spaceship, here's the Sun, here's Earth. And the Earth is 1 AU away from our Sun. And then the angle it makes is 1 arc second. So we have a definition, d equals 1 over p. So d is the distance in parsecs when p is in arc seconds. So doing the math, 1 parsec equals 3.2 light years. Does this make sense? So this is just basic trigonometry. So let me see if I can write on the slide to see if I can make it a little bit easier. So we are in a spaceship and we are far away from the Sun and Earth. So when we look back at Earth, at the Sun, this distance over here is 1 AU. So now we want to know what this distance is. So we know this angle right here is 1 arc second. And we know so we want this distance, so we want this distance. We know what this distance is, we know what this angle is. So now we can just plug it into our formula where we say d is in parsecs, and that equals 1 over p, where p is the angle in arc seconds. So solving this equation, we have 1 parsec equals 3.26 light years. Does that help a little bit? Yes, this is in the textbook. There is now a lot of nice YouTube videos explaining this as well. I know this is a bit difficult concept to wrap your mind around, but for all intents and purposes of this course, it just is all anything you need to remember is 1 parsec is 3.26 light years. Yes, I will upload the slides after class. I've already uploaded yesterday's slides as well. So another way to think about this is we know a full circle is 360 degrees. So we want to work in minutes, so dividing it with 60 gives us arc minutes. So now we need to get arc seconds. So dividing that by 60 gives us arc seconds. So 1 parsec equals 3.26 light years. So before going on to the next slide, so what do you guys think will be the next unit we are using? So going to even larger distances, we are going to kiloparsecs, and even larger, we're going to megaparsecs. So where are we in the universe? What do you guys think? Yes, we can even go to gigaparsecs as well. Yes, we are in the Milky Way galaxy. So, random question. What do you guys think is the name of our solar system? Yes, correct. We are the Sol system, so S-O-L. And the Sol system is in the Milky Way galaxy. Andromeda is the other closest galaxy to us. So usually now is where I would show a nice video of where we are in the universe. So I will give you guys a link to it after class. But if you think about where are we in the universe, this is a Google image view of the UP campus. So when we are in class, this class would have been in the humanities building. I would have shown that we are in the humanities building over here, and our nice physics building where we are is right here. So if we zoom out a little bit, we can see the entire Pretoria area where the University of Pretoria is. Zooming out more, here we are in South Africa, where you can see where the University of Pretoria is. Zooming out even more, we can see Earth. So where do you guys think this is leading? so we're leading to the universe. So we zoom out a little bit more. Here we can see planet Earth with Africa in view. Flat Earthers leave the chat, that's funny. So zooming out more, we can see Earth's closest natural satellite. That's roughly 384,000 kilometers away. Zooming out even more, we see our own solar system. Unfortunately, Pluto is not a planet anymore. I don't agree with that. I personally think Pluto should have been kept a planet due to tradition and historical reasons, but international astronomy community voted that Pluto is not a planet anymore, so now we have to go by that definition as well. So zooming out even more, here we can see we have the Sun, we have Earth, Mars, Jupiter, Saturn, Neptune, Pluto, the asteroid belt between Mars and Jupiter. We have our heliopause. We can go to the edge of our local cloud, the Oort cloud of our solar system. And here we can see Alpha Centauri, our closest star. So the heliosphere is our own solar system. So right here we get to the interstellar medium or interstellar space. So how dense is the Oort cloud? That's something I cannot say out of memory, that I have to look up for you as well. So if we zoom out a little bit, here we are in our little corner of our galaxy. So our little corner is, we're part of the Orion arm of our galaxy, but we will discuss that in other chapters as well. So that gives this perspective of how small we actually are and how big the universe actually is and how much there are to learn. So how did we get that image? This is not an actual image that was taken. This is just a graphics illustration of the data that we have, and this is how the math shows everything will look like. So zooming out a little bit more, we have the local galactic group. So this is where different galaxies are clumped together to form groups, and our galaxy, the Milky Way, forms part of the local galactic group. So here we can see which galaxies are close to us. So here we can see the Andromeda galaxy, the large and small Magellatic clouds, and a few other objects as well. So why is it illustrated as a cylindrical matter? You will learn more about this in calculus. If we use a cylinder, the math just becomes easier to get different coordinates. So the shape of the universe is a sphere. We are expanding. So this is just to make the math easier and to illustrate where we are going. So do you guys think we can zoom out a little bit further? So expanding into what? That we don't know yet. So the universe is expanding and we need to figure out what's going on. So if we zoom out more, here we can see different galaxy clusters. So all of these speckles we see are galaxies that is clumped or close together. So do you guys think we can zoom out more? So if we zoom out more, we get this representation of what our universe is. So can planets drift off their current position in the universe? Unfortunately not. Our planet is stuck in orbits around stars, but that star can wander through is orbiting the center of its own galaxy, and the galaxy is moving through the universe. So can galaxies clash into one another? So yes, galaxies can clash into one another. So currently our galaxy, the Milky Way, and the Andromeda galaxy is moving to one another, and they will collide in a couple of billion years. So are these images representative of what scientists think is out there? Yes, so this is just representative of the mathematical models we have. So question, what if the universe is a black hole? That we don't know. So before going on to the next slide, what do you guys think is the time scale of everything of this? So it's 13 billion years. But to put this in perspective, if we could shrink everything down into a calendar month, into a year, how would things occur? Things would start slowly and then speed up. So let's say the universe, the Big Bang, occurs in January. We can see the first stars and galaxies appearing around about March. Our own Milky Way galaxy will form around about May. More galaxies in June. Planets will start forming in planetary disks will start forming in August. Planets will start. Our solar system forms in September, and life begins on Earth at the same time. So in October, Earth's atmosphere becomes oxygenated. November, first complex life forms appear on Earth. Then in December, things starts to happen fast. The 19th of December, vertebrates appear. 20th December, land plants appear. 25th December, dinosaurs appear. 26th December, mammals appear. 30 December, dinosaurs becomes extinct. 31 December, humans appear. So that's just to put everything in perspective of what's happening in our universe in a time scale of a year. So everything started out slowly, and all the exciting stuff happened in the last month. How long was dinosaurs alive? A couple of million years. So how did the humans appear? That is something interesting. I'm not a biologist, so that is something the evolutionary biologists will be able to answer. But this is questions we need to answer as scientists. So going further, and we start looking at the history of astronomy. So the Chinese began with the idea of astronomy back in 2000 BC. In 1000 BC, 2000 BC, in 1000 BC, the Babylonians and the Greeks also got interested in astronomy. In year zero, Ptolemy started creating his models. Then in the year 1000, we have Tycho Brahe, Copernicus, Galileo Galilei, Johannes Kepler, Isaac Newton, William Herschel, Albert Einstein, Hubble, Carl Jansky, Grete Weber, the Hubble Space Telescope, the Chandra X-ray Observatory. So, the main idea of what happens is the Chinese started to chart stars and record our solar system and lunar eclipses. The Babylonians made accurate predictions of planets and their visibility. The Greeks developed important ideas about Earth, stars, and planets. Ptolemy wrote about Greek ideas that a sun circled around Earth. Tycho Brahe analyzed motions of planets and predicted the motions were accurate. Copernicus proposed the Sun as center of our solar system. Hans Lippershey invented telescope by placing simple lenses at the end of a tube. Then Galileo Galilei improved the telescope by making a refracting telescope. Johannes Kepler proposed planets orbit the Sun in elliptical orbits. Isaac Newton invented reflecting telescopes. William Herschel discovered the planet Uranus. Johann Galle discovered the planet Neptune. Then we have Einstein, Hubble, Koljansky, Grothe-Reber, Hubble Space Telescope, the Chandra X-ray Observatory, and that is where we are today. No, we are not supposed to memorize all of these events. This is just to show you guys that astronomy is also a historical science. So a lot of our work is built up on the previous work of previous generations. So that is why Stephen Hawking said, we are standing on the shoulders of giants. So now you are right. So now in 2021, the James Webb Telescope is likely going to be launched. So, going to the next slide, an important part of astronomy is pattern recognition. So humans have been looking up at the sky and making observations since the earliest ancient civilizations, and likely before that too. So the simple power of pattern recognition is considered the separation point between sentient and non-sentient beings. Why do you guys think this is important? Okay, long-term preservation, but to observe patterns is very important. If we can't understand patterns, then we understand what's going on around us. So something interesting about patterns. We as humans like everything to be linear, but nothing in nature is linear. Have you guys learned about that before, heard that before? So mostly everything in nature is usually exponential, but we as humans like things to be linear. So some of the patterns that started in astronomy is our solar system, Copernicus. So in 1543 AD, when Copernicus became the first person to demonstrate the math behind such an insane idea, he was universally ridiculed. In fact, the heliocentric model was so revolutionary that Copernicus was actually afraid to publicize it. However, once the idea was finally accepted, it eliminated many problems with older astronomical studies and is considered the first major realization of our place in the universe. We realized that the sun is a star, not a god, and that we aren't located at the center of the universe. So Plotme's model say that the earth is the center of everything and everything moves around us. So after looking at patterns, we realized with the Copernicus system or the heliocentric model that the sun is the center and we are moving around the sun. And this is just by observing everything and by putting patterns together. So were people punished for coming up with groundbreaking ideas? Unfortunately, yes. Back in the day, the church and religious leaders had a lot of say over what's going on. So, unfortunately, when you went against the beliefs and rules of the church, then you are wrong and you got in trouble and punished and you are arrested. You are correct, he was placed under house arrest. So, next thing we see with these patterns are Kepler's laws, and I'm all sure you are familiar with Kepler's laws. So, Kepler's laws describe how objects move in ellipses around certain bodies. We will go through this as well. But Johannes Kepler proved that planets move around the Sun in elliptical orbits rather than perfect circles. In 1609, this was revolutionary because it meant that the distance between the planets and the Sun changed over time. Finally, the world understood the reason behind seasons and the apparent motion of planets. Without these discoveries, astronomers would have had a much more difficult time trying to explain why the Sun's influence on Earth changes and why the speeds of other planets seem to vary over time. So these are a few of the important discoveries in astronomy. Is it possible to observe a change in the Sun's apparent size as the seasons change? Yes. That is also something we are going to discuss, but let me get a whiteboard. Why the apparent size changes? Let's say this is the Sun. This is our orbit around the Sun. So here we are much closer to the Sun, here we are much further from the Sun. So here it will appear that the apparent size will be bigger, here the apparent size will be smaller. And because the Earth moves around the Sun, here's Earth, this is not drawn into scale, and the Earth is canted. So if we're on this point of this part of the Sun, this part will receive the most rays, this part will receive less rays. So that is why we have summer and winter. Short and sweet of it. You guys have any questions this far? So questions, do planets have seasons? So if you have a cant of a couple of degrees, then you'll have seasons. If you don't have any cant, then there won't be a lot of seasons. So another important discovery in astronomy is Jupiter's moons. So Galileo discovered 4 moons of Jupiter in 1610 using a telescope that he designed and created himself. They were the first moons discovered that didn't orbit Earth, making them the most important piece of evidence for Copernicus' model of heliocentrism. This was tangible proof that planets other than Earth had moons and that we weren't unique as we thought. So, how do moons form? We will discuss that in later chapters as well. But when a star is formed, it has a planetary disk around it. The planetary disk forms different planets, but while planets are formed, there are still particles clumped around that planet, and that can become a moon, or a piece of the planet can break off while it's forming, and that can also become a moon. So what do you guys think is one of the next important astronomy discoveries in recent times? So is there a possibility that Earth can get another moon? Unfortunately, no. So discoveries to come is life on Mars, yes. Other galaxies is also big in important discovery. Saturn's rings is also important. But if you look at the slides, the next is Herschel's map. So astronomer William Herschel and his sister Caroline systematically mapped the night sky, listing thousands of stars and nebulae in an almost 5-decade process, published in 1834. This map revealed the shape and size of the Milky Way, which turned out to be disc-shaped rather than a sphere. He also discovered Uranus. Is it true that the moon is moving away from Earth? So yes, the moon is slowly moving a little bit away from Earth, and that is because Earth is spinning, but Earth is still losing a bit of its angular momentum. And because the moon is in an orbit and Earth's spin is starting to become a little bit slower, it creeps away little by little by little. So are stars coming closer or going further from Earth? Both is actually. Some stars move towards us, some moving away from us. But if you look at the Doppler effect, that's also something we're going to discuss later on, is the red shifts and blue shifts of the Doppler effect. So if everything is blue shifted, it's moving towards us. Red shifted, it's moving away from us. And the majority of stars in our universe is red shifted. So the next important discovery is theory of relativity. Before Einstein knocked it out of the park with his theory of relativity, the world of astronomy strictly obeyed Newton's 3 laws of motion. Everything changed when Einstein argued that motion was relative and that light could be affected by gravity. The possibility that mass could warp space-time and that large enough masses could even bend light shook the scientific community. Because light was considered an absolute constant, the theory revolutionized astronomy and solved many problems that had been deemed impossible with Newtonian confining laws. Then we have the universe is expanding. So when Edwin Hubble told the world that the universe is expanding, it was groundbreaking, to say the least. After tracking the movement of other galaxies, which he was also the first to discover, he concluded that they are moving away from us, while also constantly accelerating. He also concluded that most of the nebula visible in the night sky were actually galaxies. This provided further evidence to support the theory of the Big Bang and changed our concept of the universe. So, sir, what is meant by space-time? Okay, so the easiest way to explain space-time. We operate in 4 dimensions. So if we want to know where something is, we need an X, Y, and Z coordinate of the location. So that's true for everything in the universe. That's a universal law of nature. But there's also a 4th coordinate called time. So we have X, Y, Z, and time. And with that, we know where everything is in the universe. And wrapping those together is space-time. So when you said galaxies are moving away from us, does the us mean the Milky Way or Earth? That is both. So when you look at a larger scale, we talk about the galaxy, but we use Earth as well. And then a recent important discovery is the cosmic microwave background radiation. We will discuss this better in the next lecture, but uniformly defined radiation that fills the universe was discovered quite accidentally by 2 Bell telephone employees in 1964 while working on satellite communication. Since light from an object 1 light-year away takes 1 year to reach Earth, the cosmic microwave background functions like a snapshot of the universe. The implications of this discovery were profound, since the uniformity of radiation appears to confirm the notion that the universe originated in a single event from which everything else flows. This fact supports the theory of expanding universe and therefore the Big Bang. Yes, so the static we see on old analog TVs is cosmic microwave background radiation. I will talk about that in depth in our next lecture. So another big important discovery are extrasolar planets. So an extrasolar planet, also known as an exoplanet, is a planet found outside our solar system. The existence of exoplanets was not all that surprising, but the method by which they were discovered has changed the course of astronomy. Nearly 3,000 exoplanets have been discovered since 1988. Roughly 1 in 5 Sun-like stars have an Earth-sized planet within the habitable distance from the star. Assuming there are 200 billion stars in the Milky Way, that would mean 11 billion habitable Earth-like planets in the Milky Way alone. And then the most important astronomy in the last 3 years is the first image of a black hole. So I'm going to end off tonight's lecture with the following quote of Neil deGrasse Tyson. The molecules that comprise our body are traceable to the crucibles of the centers of stars. These atoms and molecules are in us because, in fact, the universe is in us. And we are not only figuratively, but literally stardust. And people still say there can't be possibility of other life forms. True. So, ladies and gentlemen, this was tonight's lecture. I hope you guys enjoyed it. If you have questions, you are more than welcome to answer. I will remain active for a few more minutes if you guys want to answer questions. If there is no more questions, you guys are more than welcome to log off. It's a pleasure. So question, what can we do next as in textbook work? So for the next week's work, we're going to look at chapter 2 and 3. So how do we destroy the universe? That is actually a good question. I don't know.
For mathematics will we be using in this module?
This math it will be straightforward high school math. So it's just going to be a bit of trigonometry, multiplication, division, and algebra.
What are we going to use it for more specifically, out of curiosity?
More specifically, I'm going to ask you to calculate the distance of certain objects. So I'm going to give you a few formulas, then you have to calculate the distance in astronomical units and parsecs, be able to convert between astronomical units, light years, parsecs, and then also just a few temperature questions, and then how to calculate the brightness of objects.
Okay, cool, thank you.
It's a pleasure. So are there exercises we can do? So currently no exercises yet because we're still going through the background. But as soon as we get to exercises, I will tell you which examples in the textbook you can go through, and then I will also give you a few quizzes to help you prepare for the exercises and exam. So I have a small technical error. I cannot put my details for the WhatsApp group in a Google Doc. What can I do? If you can't put it in, just please send me an email. It's a pleasure. So the quizzes won't be weekly. There won't be a lot of quizzes. I'm just primarily going to use these quizzes to see if you guys understand the work that we covered. So I know how I can adjust my teaching method so you guys can, so now I can teach you guys better and where you are struggling with the work. And it also gives you gives you guys an idea of how I would ask questions. So the WhatsApp group is not active yet. I'm still waiting for everyone to fill in the form. So currently, if I look at it, we have about 68 people that filled in the form. We are currently 136 people registered for the course. So I still need more than half of the students' details. So where can you fill in the form? I have uploaded the link to announcements on ClickUp, but I will give you the link now as well. Here is the link. It's a pleasure. And I've also uploaded, because I see there's some student that doesn't use WhatsApp, so I've also created a Discord channel that you guys can use to communicate as well. So explain the cosmic microwave background again. That's something I will discuss in the next lecture. But the cosmic microwave background is basically everywhere in the universe we pick up the frequency. It's roughly sitting at 22 megahertz. We pick that up everywhere. Doesn't matter where we look in the universe, we see this signal at 22 megahertz. If you have your old analog TV and you try to search for channels and you see that snowy, speckled stuff between channels, that is the cosmic microwave background that's being picked up by the analog antenna of your TV. If you look at your radio, if you search between stations and you hear that sound, that is the cosmic microwave background that we are also picking up on radio. So it doesn't matter what we do, we see it everywhere. That was accidentally discovered. And what it actually is, that is the traces of the Big Bang we are detecting, is the sweet and short answer of it. It's a pleasure, but we will discuss the cosmic microwave background radiation thoroughly in our next lecture. It's a pleasure. So if you guys have no more questions, have a great evening. Good luck with the rest of your classes and modules. If you have any questions, please contact me. Otherwise, I will see you in next week's class.